Between San Diego and San Francisco, there is a front line that has been active every single day for over 20 years. No ceasefire, no seasons, no negotiation. Roughly 30 million soldiers die on it every year, fighting over a border that has barely shifted in decades. The soldiers are 3 millimeters long. They belong to two Argentine ant supercolonies that are genetically almost identical. They differ by a fraction of a single hydrocarbon on their exoskeleton. That fraction turns a sister into an enemy. One colony stretches from San Diego to San Francisco. The other occupies a small enclave near Lake Hodges. Where they touch, the killing doesn't pause. Not for drought, not for winter, not for anything. And this is just one border. The same species, Leinpathema humile, runs a supercolony across 6,000 kilometers of the European coastline, from Portugal to Italy, with its own active war fronts. By casualty count, by duration, by the number of bodies fighting at any given moment, these are the biggest wars on Earth. And the thing that makes them so enormous is the same thing that makes them impossible to end. Every ant colony has a chemical barcode, a waxy layer of cuticular hydrocarbons on the exoskeleton. When two ants meet, they tap antennae. If the hydrocarbons match, sister. If they don't, enemy. In their native range along the Paraná River basin in South America, Argentine ants are genetically diverse. Their colonies are small, fiercely territorial, and fight each other constantly over distances of a few hundred meters. Evolution keeps them in check. But when human cargo ships carried Leinpathema humile to California, Europe, Japan, and Australia across the 19th and 20th centuries, something broke. The founding populations were tiny. They passed through a genetic bottleneck and lost the diversity needed to produce unique hydrocarbon signatures. The result? Billions of ants, spread across thousands of miles, that smell the same. Pick up an Argentine ant in Portugal and drop it into a nest in Italy, accept it as family. Take one from San Diego and place it in a colony in Japan, welcomed. Not because they recognize each other, because they can't tell each other apart. That is a supercolony, a single chemical identity stretched across continents. Inside it, perfect cooperation. But at its edges, where it meets a second supercolony with a slightly different barcode, war. In Southern California, the very large colony borders a genetically distinct group called the Lake Hodges colony. The chemical difference between them is microscopic. The violence is not. 30 million dead every year, and the front line has barely moved. Forget what you think ant fighting looks like. Argentine ants lost their stingers entirely. Evolution traded the ability to inject venom for something more effective against other ants. Aerosolized chemical weapons, delivered at contact range. When an Argentine ant engages an enemy, it performs a behavior called gaster bending. It curls its abdomen forward beneath its body and wipes a secretion from its pygidial gland directly onto the enemy's antennae and joints. That secretion contains two compounds, dolichodial and iridomyrmecin. Dolichodial is a localized toxic irritant. It burns. Iridomyrmecin does something worse. It scrambles the enemy's chemical senses, effectively blinding it, while simultaneously acting as a recruitment beacon. Every nearby nestmate detects the iridomyrmecin cloud and converges on the exact location of the fight. One engagement becomes 10, 10 becomes 100. The battlefield generates its own reinforcements. But here is the part that makes this system quietly horrifying. Every living ant is coated in triglycerides, fatty acids that accumulate on the exoskeleton and smell, to other ants, exactly like a decomposing body. The only reason a living ant isn't seized and dragged to the refuse pile by its own nestmates is that its pygidial gland constantly secretes iridomyrmecin to mask the death scent. When an ant dies in combat, or simply exhausts its chemical reserves while fighting, the iridomyrmecin mask fades within about 40 minutes. The raw triglyceride signature surfaces, and passing nestmates will grab it, sometimes while it is still alive and twitching, and carry it to the graveyard. The chemical system that calls for backup is the same system that keeps you from being buried alive. Combat drains both. Here is the problem with being an ant soldier. Your enemy is nearly indestructible. Centrifuge testing on American field ants measured the tensile force needed to rupture the neck joint, the weakest structural point on the body, where soft connective tissue meets hard exoskeleton. The result? The joint holds between 3,400 and 5,000 times the ant's own body weight before it fails. A single ant cannot generate anywhere near that force through its bite alone. One-on-one instant kills are effectively impossible. So ant combat doesn't look like a fight. It looks like a construction problem. Multiple workers swarm a single target. They latch onto mandibles, legs, antennae, whatever they can grip, and walk in opposite radial directions, stretching the enemy's limbs toward their absolute tensile limit. The victim is pinned in place, completely immobilized, held like that, sometimes for hours, until a larger major worker arrives to slowly cleave or dismember the captive. Not fast, not efficient. Geometry performed on a living body, until the physics finally give. And in weaver ants, Oecophila smaragdina, this cooperative force gets even more extreme. In most animal groups, adding more individuals to a pulling task makes each one lazier. That phenomenon has a name, the Ringelmann effect, social loafing. Weaver ants defy it, completely. As team size increases, each individual ant actually doubles its pulling force. They achieve this through a biomechanical strategy called the force ratchet. Ants at the front of the chain actively pull, while ants at the back lock their tarsi into the substrate and act as passive frictional anchors. The pulling force is stored in the structural chain of the insects themselves. The result is a biological winch that can tear apart prey many times the size of any individual in the chain. The physics of ant war are not about strength. They are about cooperative patience. In 1916, a British engineer named Frederick Lanchester published a set of equations to model combat attrition. One of them, Lanchester's square law, predicted that in disorganized melee fighting, the numerical size of an army provides a squared advantage over the fighting power of individual soldiers. Double your army, and your combat advantage doesn't double. It quadruples. In 2024, researchers formally applied Lanchester's equations to ant warfare for the first time, and the ants followed the math perfectly. In open terrain, a larger force of small, individually weak ants overwhelms and destroys a smaller force of larger, heavily armored ants. Every exposed surface of the defender is attacked simultaneously. Individual size, armor thickness, mandible strength, all of it becomes mathematically irrelevant against sufficient numbers. This is why tiny, 2mm Argentine ants systematically eradicate much larger native species wherever they invade. Not through superior biology, through superior arithmetic. But terrain changes the equation. When the same battles were modeled in complex environments, tunnels, narrow passages, cluttered ground, the square law advantage collapsed. A smaller force of specialist fighters in a choke point neutralized the numerical superiority entirely. A squad of large soldiers in a tunnel, repelling an army 10 times its size, the ant equivalent of Thermopylae, is not a metaphor. It is a mathematical prediction that has been tested and confirmed. Every ant battle is a math problem. The variables are numbers, terrain, and time, and the answer is always bodies. Not all ant wars are fought over territory. In the forests of Europe, redwood ants, Formica polyctena, build enormous mound nests and wage massive territorial conflicts every spring. But these spring wars are not primarily about borders. They are about food. Early in the season, external insect prey is scarce. Caterpillars haven't hatched. Aphid colonies haven't matured. The larvae are growing, and they need protein, enormous amounts of it, and there is almost none available in the forest. So neighboring colonies go to war, and then they eat the dead. Research on Formica polyctena found that up to 86.3% of the colony's protein intake during early spring consists of butchered rival ants. Cannibalistic necrophagy, the systematic consumption of dead members of the same species, is not an anomaly. It is the primary nutritional strategy during the most critical growth period of the year. The wars end when they become unnecessary. Once caterpillar populations rise and aphid honeydew becomes abundant, the cost-benefit math no longer favors combat. Fighting stops, not because the ants made peace, because the grocery store opened. And the absolute limit of this biological pragmatism was documented inside an abandoned Soviet nuclear weapons bunker in western Poland. Over a period of years, more than 1 million Formica polyctena workers fell through a rusted ventilation pipe into a pitch-black, freezing concrete chamber. No light, no external food, no way out. They survived. Researchers found the bunker floor carpeted with roughly 2 million dead ant bodies. Fluorescence-based digestive tracking confirmed that the living colony had sustained itself entirely through the consumption of nestmates who died from attrition. The dead fell, the living ate. The colony persisted. If ant war is this expensive, if every engagement drains chemical reserves, risks permanent injury, and can last hours, then which ants actually fight? Not the young ones. Research on red imported fire ants, Solenopsis invicta, found that colonies preferentially deploy older, more expendable workers to territorial boundaries and aggressive encounters. Younger workers are held back for brood care, foraging, and nest maintenance. The colony is not random about who it sends to die. It sends the individuals closest to the end of their productive lifespan, the workers whose remaining contribution to the colony is lowest, the ones whose loss costs the least. This is not a conscious decision by any individual ant. It is an emergent pattern, the result of behavioral thresholds that shift as a worker ages. Older ants are more responsive to alarm pheromones, more likely to move toward the source of conflict, more likely to engage. Evolution built a system where the ants most likely to fight are the ants the colony can most afford to lose. And if a worker survives the front but comes back damaged, missing a leg, an antenna, part of a mandible, the data is clear. Injured workers have shorter remaining lifespans and a reduced tendency to take future high-risk assignments. The colony does not repair them. It does not compensate. It simply uses them less. A damaged soldier is a diminished investment, and the colony's chemical logic treats it accordingly. There is one more layer to why these wars never stop. You might expect ants to reserve their worst aggression for unfamiliar invaders, strangers whose chemical signatures are the most alien. In many vertebrate territorial species, that is exactly what happens. Biologists call it the dear enemy effect. Known neighbors are tolerated because the cost of constantly fighting them outweighs the benefit. Highly territorial ants do the opposite. Research on weaver ants and wood ants documents what is called the nasty neighbor effect. Colonies direct exponentially higher aggression toward established adjacent colonies than toward unfamiliar wanderers. The neighbor is not tolerated. The neighbor is the primary threat, because the neighbor is competing for the exact same food, the same aphid colonies, the same foraging trails, the same nesting substrate. A stranger might pass through. A neighbor will drain your resources forever. The colonies most likely to fight are the ones that share the longest borders, and the wars most likely to escalate are the ones between opponents who cannot move away from each other. The Argentine ant supercolony borders are the ultimate expression of this. Two genetically distinct blocks, pressed against each other, sharing a permanent boundary, competing for identical resources, with no mechanism for recognition, no mechanism for negotiation, and no mechanism for retreat. 30 million dead every year, and the front line does not move. There is no treaty, there is no surrender, there is no tired general who decides the cost has become too high. An ant colony does not experience war the way a nation does. It does not accumulate trauma, it does not weigh history, it responds to chemistry. The pheromone gradient at the border, right now. The hydrocarbon signature on the antenna of the ant in front of it, right now. The nutritional status of the brood chamber, right now. Every decision is local, every engagement is the first engagement. The war has no memory. And because the colonies on both sides of the border continuously produce new workers, expendable, chemically identical, behaviorally primed, the armies never deplete. The dead are replaced before the chemical stain of the last fight has faded from the soil. This is not cruelty, it is not tragedy in the way we understand it. It is a system that works, in the narrow sense that the genes behind it keep replicating. The colony that fights holds its territory. The colony that stops fighting loses it. And losing territory means losing the food that feeds the queen, that lays the eggs that build the next generation of soldiers. Evolution did not build a war that ends. It built a war that persists, because persistence is the only strategy that survives. Somewhere between San Diego and San Francisco, the front line is exactly where it was yesterday. The ants on one side cannot tell the difference between today's enemy and last year's. The ants on the other side cannot either. 30 million more will die this year, and neither side will notice.